Hi everyone, I'm Daniele Rigon from the Department of Industrial Engineering of the University of Padua. The other authors involved in this work are Professor Ricotta and Professor Giovanni Meneghetti. And today I'm going to talk about the state of the art of the structural durability of 3D printed virgin and recycled ABS and polypropylene compounds. The presentation is divided in four main parts. So first, I introduce the motivation of this work. Then I'm going through an introduction about the considered 3D printing process, so the fused deposition modeling. After that, I present you the static and fatigue result taken from the literature of the following material produced by injection molding and fused deposition modeling. So the considered materials are ABS, virgin and recycled, polypropylene, virgin and recycled, and finally a short glass fiber reinforced polypropylene with 30% in weight of fibers, virgin and recycled. And finally, I'll draw the conclusion. Let's start with the motivation of this work. This work is a first point of a research project that we have in collaboration with Electrolux, in which the aim is to reduce the waste of plastics in white goods industry. The main goal of the research project is to study the structural durability of two recycled plastics in order to substitute some components with new ones produced by additive manufacturing and optimized by means of topology optimization. The considered material are a recycled ABS and a recycled polypropylene calcium carbonates compounds reinforced by short glass fiber. So the presentation deals with the state of the art of the structural durability of ABS and polypropylene compound produced by fused deposition modeling. The fused filament fabrication or fused deposition modeling is an extrusion process where the object is built by depositing melted material layer by layer. So the raw material is rolled in a spool and pushed towards a printer extruder by means of drive wheels. These drive wheels control the material flow inside the printer extruder, where the material is heated and then deposited by a nozzle. So the main advantages of this process is to produce components with complex geometry, where the mass can be minimized by adopting topology optimization in the design phase. A wide choice of commercially available materials, easily changeable materials, and also a low temperature operation. The main disadvantages of this process are high anisotropy with respect to the build direction, the surface quality of the component in the as-built condition, the imperfect sealing between layers and tool paths, and the necessity of support structures in some parts of the component. Finally, the process takes long times for produce a massive component. According to the aim of this work, we collected static and fatigue test result on an ABS, polypropylene and short glass fiber reinforced polypropylene with 30% in weight of fibers. The specimens were horizontally built with respect to the build orientation with an infill density of 100%. Furthermore, the infill pattern analyzed were 0 degree, 45 degree, and 90 degree ones, and the combination of 0 and 90 degree, and the same combination rotated by 45 degrees. In this slide, we can see a graphical representation of the comparison that we can make on the data available in the literature. Regarding the static properties of the ABS, we can compare virgin and recycled material produced by both injection molding and FDM process. The same can be done with with the polypropylene compounds found in literature, but there is a lack of data regarding the recycled polypropylene compounds produced by FDM. Let's start with the static properties of the ABS. Here we have the list of references over which the data were taken, and here we have the bar graph with the relevant results. The gray band is the scatter of the UTS of virgin injection molded ABS, and starting from the left we have the recycled ABS produced by injection molding, which has the same value of the virgin reference materials. The other bars are related to the virgin ABS produced by FDM with different raster orientation. The best performance about this technology were obtained with the 0-degree orientation of the raster, and the lowest one was obtained on the 90-degree orientation. The last bar is related to the recycled ABS produced by FDM. The UTS of this material is surprisingly close to the reference virgin injection molded ABS. However, no information about the process parameter in order to produce this material were reported in the paper. Regarding the static properties of polypropylene, here we have the synthesis of the results. By analyzing the injection molding, the recycled polypropylene has a 30% lower UTS than the virgin material. By comparing the virgin polypropylene produced by injection molding and FDM, no difference can be observed in terms of UTS, but if we analyze the virgin FDM, we can see a slight influence of the raster orientation on the UTS, where the best performance were obtained with a raster orientation of 0-degree, and the lowest one is obtained on plus minus 45 degrees. Finally, we have the static properties of PPGF 30. Analyzing the injection molding virgin PPGF, we can observe a different value of the UTS due to the different fiber lengths in the material. The relevant recycled PPGF 30 produced by injection molding show the UTS lower than the lowest virgin injection molded PPGF. No information about fiber length was reported in the original paper, so no further conclusion can be drawn regarding this. By analyzing the FDM virgin PPGF, even in this case, with a raster orientation of plus minus 45 degrees, the UTS is lower than the lowest virgin injection molded PPGF. Now let's move on the fatigue test results. Here we have the same flow charts which identify the data available from the literature. About the ABS, only virgin material can be found in the literature, so we can compare just the technology used. For the polypropylene compounds, we can compare only the virgin and the recycled injection molded materials. Starting with the virgin injection molded ABS, here we have the fatigue test result taken from several papers found in literature, expressed in terms of stress range against the number of cycles. Now, from different papers, we had the fatigue test result related to the virgin FDM ABS. As you can see, the best performance in terms of fatigue strength are obtained for a 0-degree orientation, and the lowest one was obtained from for a 90-degree orientation. Regarding the polypropylene, just the comparison between the virgin and the recycled injection molding material can be done, and here we see the difference in terms of fatigue strength with respect to the virgin and recycled polypropylene. Finally, we have the fatigue test result related to PPGF 30. Two different fiber lengths were considered in the virgin injection molded PPGF, and the relevant results are the blue and the yellow ones. The recycled PPGF 30 were reported in the gray square marker. As you can see, the recycled PPGF has approximately 30% lower fatigue strength with respect to the virgin material. At the end, we can draw the following conclusion. So the state of the art of the static and fatigue properties of virgin and recycled material produced by injection molding and FDM was presented. Regarding the static properties, the recycled ABS showed comparable UTS with respect to the relevant virgin ABS, whereas the other recycled material analyzed showed UTS approximately 30% lower than the relevant virgin ones. For the FDM materials, it has shown that lower UTS with respect to the injection molded ones, over which the best UTS was obtained for flat-oriented specimen with a raster orientation of 0 degree. Regarding the fatigue strength, the recycled material show lower fatigue strength than the relevant virgin ones. FDM, the material that show lower fatigue strength with respect to the injection molded one, over which the best fatigue strength was obtained on flat-oriented specimen with a raster orientation of 0 degree and plus minus 45 degrees. Thank you for the attention.